So today we'll be talking about kinematics for bike gears by Jonah Johnson, Preston Leigh, Chandu Wanliang Xing, and Jiang Wang. And today only Jonah, Preston, and I will be presenting. Next slide, please. So I am completely addicted to very large bicycles, and I want to figure out what type of gear system I should have on my 100th bike. So I hired some help. I want a single pedal gear and 3 rear gears for it, as well as 3 large wheels of my choice. Next slide. So, since I like bikes and the prompt was about a bike, we were inspired to do our presentation on a bike. We will be using a bike that has 1 big gear in the middle of the bike and 3 different giant tire sizes, as well as 3 different gear sizes in the back of the rear tire. Using rotational kinematics to figure out how different size tires and gears affect the speed of the bike. All right, next slide.
All right, so we have a few assumptions and related concepts here. As with every physics problem, we'd love to ignore air resistance. And the spokes on the gear, we're just going to ignore and pretend that it's completely frictionless, or the opposite of that. So the number of teeth in the gear just do not matter. Everything is turning clockwise, and nothing slips. The mass of the gears and tires are uniform. There's also only going to be 2 gears at a time in this as compared to the typical 3 or 4 of a mountain bike. And in order to ignore friction of the ground, we're going to assume Chandu is propping up the bike and testing the speeds. And then related concepts, we're going to be using rotational kinematics and kinetics, bikes, and gears. So what we know and what we don't know. We know the pedal speed is going to be a constant 6.3 radians a second. We know the pedal gear radius, the radii of the 3 rear gears, and the radii of the 3 wheels. What we don't know is the speed of each wheel with their respective set of gears. And here are the variables we're going to be using. We're going to ignore coefficient of rolling friction again. We got the angular speed, which is in radians a second, the angular acceleration, which is radians in seconds squared, and the radius r in meters. So we got the schematic of the bike, and we can see, again, the constant angular velocity, the front gear size, the bike size tires, and the rear gear size. And the reason why we have these tires so big is because we thought it'd be funny.
So I'll be speaking for the Chinese students for the next few slides. So here's a close-up schematic of the system. The RT is the radius of the main gear, the front gear, and W is equal to 6.3 rads per second. So what they did is they solved for the velocity of that front gear, which translates into the chain, because the chain is enacting upon the back gear whatever the front gear enacts on the chain. So they said that V is equal to 1,360.8 millimeters per second. And with that, they have the equations below to solve for the angular velocity of each of the gears, and then an equation to solve for the velocity of each of the tires with those angular velocities. So we can go to the next slide. So here are their calculations for the first tire. As you can see, they used V rather than the angular velocity equation, which is W1 times R1 is equal to W2 times R2. But as you can see, they have the speed for the smallest tire with the big gear, medium gear, and small gear. And the next slide. And then they have this again for the medium tire. They used the same equations and solved with all 3 different gears. Next slide. You can go to the next slide. So to simplify all of their calculations and to kind of show the work a little bit more, I created these tables just kind of outlining what happens. We have our given conditions on the left there. And so first we had to solve for the angular velocity of each of the gears. So in there I put the angular velocity equation using the main gear that the pedals are acting upon with each of the individual gears, the small, medium, and large, and solve for the angular velocities of the small gear, medium gear, and large gear. As you can see, first one for the small gear is about 27.2 rads per second, medium gear is about 19.4 rads per second, and large gear is about 15.1 rads per second. And then with those angular velocities, we're able to use those angular velocities times the radius of each of the bike tires to find the velocity of the tires. So you can see with the large tire and the small gear, it has the greatest velocity. And as you get larger gears in the back connected to the tires, the slower the bike actually goes. So the slowest would be having a large gear in the back and having small tires. So Preston, if you want to explain the conclusion a little bit better.
All right, so in conclusion, our good friend Chandu has figured out, with our help, what gears and what tires he wants to go the fastest and the slowest. So we learned that as the gear gets smaller, the speed of the corresponding wheel increases, as long as you keep a constant acceleration or constant velocity. And as the wheel size increases, so does the speed of it with any of the gears. And thus, the fastest set of gear and tire is the biggest tire with the smallest gear. And here are our sources. Thanks for listening.